Good morning. Welcome to the second video on quadratics. So we introduced it last lesson. Today we're going to take things a bit further. We're going to have a look in more depth at completing the square. In particular, we're going to use the idea of completing the square to prove one of the most famous equations in maths, which you may have seen from the age of maybe even 30 and upwards. It's the quadratic formula. So we're going to use completing the square to even prove that to you. And then we can have a look at some worked examples as always. But before we do anything, as you probably know by now, we're going to do 4 warm-up questions. So here they are. Try them yourselves before you look at the solutions. When you're ready, press play and carry on with the video. So pause it now and try them. Press play when you're ready. So, okay, let's have a look now at the solution to question 1. So question 1, we're asked here to find the exact solutions to this following equation. So x minus 3 all squared equals 11. So the first thing we must do is to square root both sides. If we do that, we get that x minus 3 has to be plus or minus the square root of 11. We need to make x a subject, and so we just add 3 to both sides, and we get that x must be either 3 minus the square root of 11, that's the first root, or it might be that x is equal to 3 plus the square root of 11. And that's the second solution. Question 2, we need to write this in the following, so it's p brackets x plus q all squared plus r, where p, q and r are integers to be found. Don't let this one throw you. If you have a look at this form here, it's just essentially completing the square for this. So what we do, we complete the square when the coefficient of the x squared is unitary. So we need to factorise out this 2 from anything to do with the variable. So we factorise out the 2 from the x squared, and we also need to divide this by 2 as well, therefore. So the minus 12 becomes minus 6x. We're going to leave this plus 3 at the end for now, so we're not going to worry about this plus 3 until the last step. Then in these big squared brackets, we're going to complete the square on the x squared minus 6x. So we half the coefficient of the x, half of minus 6 is minus 3, square all that, and then subtract away the second term all squared. Minus 3 all squared, like we saw last lesson, is going to be 9, so we minus off 9. Still all in the big squared brackets, very important. And finally, plus 3. So all we're doing so far is completing the square on this bit here, which becomes this. So we now can expand this out. So we have 2 lots of x minus 3 all squared, and 2 lots of minus 9, that's going to be minus 18, and again with this plus 3 at the end. So now the final step, just simplify it all. So 2 lots of x minus 3 all squared, minus 18 add 3 is minus 15 overall. And so that is the final answer. So p is 2, q is negative 3, and r is negative 15. The question doesn't say you need to state that, so we're okay just to leave this as it is. Question 3, we need to write square root of a half in this particular form where a and b are rational. Rational, this is a big clue, this word. We're going to rationalise the denominator. So first of all, we need to remember when we have a square root of a fraction, we can square root the top and square root the bottom separately. So this is the same as root 1 over root 2. Square root of 1 is just 1. Square root of 2 we leave like this because this is irrational. But we need to have this in the form where this is b, where this is rational, so we need to rationalise the denominator. So we're going to multiply the top and the bottom of this by the square root of 2. The top then becomes 1 multiplied by the square root of 2, which is just the square root of 2. Root 2 times root 2 is 2. And so a and b are both 2. Finally, for the warm-up, question 4, we need to solve this equation not by using a calculator or anything else, but by showing we know how to complete the square. And so what we're going to do first of all is factorise out any coefficient of the x squared. So we need to factorise out this 3. And in big square brackets, we're going to put x squared, and to get minus 12x, inside these big squared brackets, we need minus 4x. We're going to leave this 11 on its own. So plus 11 equals 0. We now complete the square on this bit on the inside. So all we're doing is rewriting this bit here like this. So now inside these big squared brackets, we can complete the square on x squared minus 4x. So that's going to become x minus 2 all squared. Then we need to minus off this 2 squared. So when we minus off 2 squared, that's the same as minusing off 4. Again, leave this 11 on its own, equals 0. So all I've changed at this step is I've changed this into this down here. This bit now we can now expand out, and so we have 3 lots of x minus 2 all squared. 3 times minus 4 is minus 12, and again there's plus 11 at the end, equals 0. We can now combine this number into just 1. Minus 12 plus 11 is minus 1. So if we add 1 to both sides, we see that 3 lots of x minus 2 squared must equal 1. If we divide through by 3 now, we'll see that x minus 2 all squared must be equal to 1/3. I'll just give myself a bit more space so you can see it all on the same page rather than me having to scroll down. So if I just take what we have here, then start a new column over here. So what we can do at this stage is we can square root both sides of this equation. So we'll then have x minus 2 equals plus or minus, be careful, always plus or minus, the square root of 1/3. Like I mentioned in warm-up question 3 though, we can think of the square root of 1/3 as being the square root of 1 on top, which is 1, the square root of 3 on the bottom, which we just leave as root 3. We can then rationalise this denominator by multiplying both top and bottom by root 3. And if we do that, on the top, we're going to have 1 multiplied by root 3, which is obviously just root 3. On the bottom, root 3 times itself is going to give us 3. So then what we're going to have as a final step is that x, we add 2 to both sides, so either x is going to be 2 minus root 3 over 3, which I'm going to leave as 1/3 root 3 like so, or we could have that x is 2 plus 1/3 of root 3. So I'm writing it as 1/3 root 3 instead of root 3 over 3, because now it just looks in this form more nicely. So we can see that a is 2 and b is either minus 1/3 or positive 1/3. So let's get straight into some worked examples to consolidate what we were doing last lesson in terms of completing the square. And so let's apply this now to completing the square in order to solve some quadratic equations. So, part A. What we need to do first of all is to complete the square on this bit of the equation. And so what we're going to have first of all is x in the brackets, half of this coefficient, half of it becomes 4, and all squared. We subtract off this term all squared, so we minus off 16. So this bit in yellow becomes this bit here. And finally, plus 10 equals 0. So we'll leave the x plus 4 all squared as it is for now, and think about these numbers. Minus 16 plus 10 is minus 6. So we can add 6 to both sides, and we get this. We can now square root both sides, and we then get that x plus 4 must be either plus or minus the square root of 6. The square root of 6 is a third. We can't simplify this any further without it being a approximate decimal. So if we finally subtract 4 from both sides, we'll see that x is going to be either minus 4 minus root 6, or x is going to be minus 4 plus root 6. So we have two solutions to this one. For part B, what we need to do first of all is to bring everything to one side of the equation, so the right-hand side is equal to 0. So if we subtract away 35 from both sides, what we're going to have over here is 3 minus 35, which is minus 32. All that's equal to 0. If we now spot, all of these terms here have a common factor of 2. So just to make things easier, we can divide through this whole thing by 2, which gives us x squared minus 6x minus 16 equals 0. Now these questions does say in no uncertain terms solve them by completing the square. So in a different colour, in like a little thought bubble, I just want to remind you that this could be factorised in a simpler way, but we're going to complete the square so you can see that it's consistent with doing it the way we've done before. So we could think of, if it was a different question, if we didn't have to complete the square, we could think of just two numbers that multiply together to give negative 16, and when we add them give us minus 6. In other words, we could say these numbers are 2 and minus 8. So what we could have done is factorise this into a positive 2 and a negative 8 equal to 0. Then by factorising, we would have seen that x equals either minus 2 or positive 8. So I'll put this in a little sort of thought bubble because the question doesn't allow us to do that. We need to complete the square. And so if we continue where we left off and see if we can arrive at this via completing the square, x squared minus 6x, we're going to complete the square on this part of it. So what we're going to do is put the x in brackets, we half this coefficient, so minus 6 becomes minus 3. We square all that, then we subtract off this last term all squared. Minus 3 all squared is minus 9. So we change this bit into this form, and at this stage we leave that minus 16 on its own. So let's neaten this up slightly. So we have x minus 3 all squared. Minus 9 minus 16, that's minus 25. And so we can add 25 to both sides to arrive at this. We can now square root both sides. Now 25 is obviously a square number, so square root of 25 is 5, and be very careful to remember plus or minus bit in front of it. Now if we add 3 to both sides, we arrive at our solutions. So therefore, either x is going to be 3 minus 5, which is minus 2, or x is 3 plus 5, which is 8, which is exactly what we arrived at over here. So as you'd expect, the answers are the same, just using a different method. So sometimes one method is better, other times the other method is preferable. So that's how we do it by completing the square. Part C now. Same idea to part B in that we need everything on the same side of the equation. And so if we take this and subtract 2x and subtract 1 from both sides, we'll arrive at 2x squared minus 8x plus 7. Set that equal to 0. And so what we need to do now is we try to complete the square on this part of it. But like I've said before, when we're completing the square, we need to make sure that the coefficient of the x squared is 1. So we need to factorise out a 2 from all of this. So we then have x squared minus 4x. Leave a plus 7 on its own. And so this bit just becomes what we have here. We now complete the brackets, sorry, not complete the brackets, we complete the square on what's inside of these squared brackets. So we can have two lots of x, half this coefficient, half of -4 is -2, square all of that, subtract away the -2 squared, -2 squared is 4, and so this bit inside the brackets here becomes what we can see here. And then plus 7, of course, that equals 0. We can now expand this out, so we have two lots of x minus 2 all squared. 2 times -4 is -8, plus 7 equals 0. Quite a long slog this one, but we're going to get there. So -8 plus 7 is -1. So if we add 1 to both sides, we get that this is equal to 1. If we divide through by 2 now, we'll see that x minus 2 all squared is equal to 1/2. Now, we can square root both sides at this stage. So x minus 2 must be plus or minus the square root of 1/2. And I'm going to slightly cheat now. I'm going to use warm-up example 3 to remember what plus or minus √1/2 was. We worked out that √1/2 is the same as 1 over √2, which is the same as 2 over √2 when we rationalise it. And so this thing here is the same as plus or minus √2 all over 2. Now, if we add 2 to both sides, we've solved it. So therefore, x is going to be, well, if we add 2 to both sides, we have 2 plus or minus √2 over 2, but we can get it all over this common denominator of 2. So 2 is the same as 4 over 2. So we can put this 2 as 4 over the common denominator of 2. So either x is going to be 4 minus √2 all over 2, or x is going to be 4 plus √2 all over 2. So let's have a think about now the quadratic formula. So the quadratic formula, what is it? I'm sure you will know, of course, but just a bit of introduction for you. The quadratic equation is the standard form of ax squared plus bx plus c equals 0, where a, b and c are parameters. So a, b and c aren't variables, so for any one equation they're constant, they're fixed. But parameters mean that between one equation and the other, a, b and c may change, but they're fixed for any one particular equation. So they can change, not within any equation, they're not a variable, but they can alter from one equation to the next, where this equation has the same exact form. So you will have seen this before. I'd struggle to believe you if you're doing A level and you've not seen this. So where on earth does this come from? So it does look quite strange the first time you come across it. I was just shown it without any proof initially, and I was like, well, how does that make any sense? So until you've seen a proof of it, it does seem magical that it works at all. But actually the proof is relatively straightforward. It's not much more than just completing the square. So let's prove it. So what I'm going to do first of all, I'm going to set out my stall by saying that we'll just have ax squared plus bx plus c equal to 0, where a itself is not 0. So what we can do, we can complete the square on this, but like I mentioned before, if we're completing the square, we've got to make sure this coefficient of x squared is 1. So to get rid of this a, what we could do is we could just divide through by a. So if we just divide this whole thing through by a, here's what we'll end up arriving at. We'll have x squared, bx becomes bx over a, c becomes c over a, and the 0 divided by a just stays as 0. So we've got it in this form now. Now we can complete the square on this. So now if we just go and complete the square on this, we're going to complete the square just on this part first. We're going to leave the c over a as it is. So the same idea applies, just this is more algebraic than normal. So we put the x in the brackets, and we halve the coefficient of the x. The thing before the x now is b over a. If we halve b over a, that becomes b over 2a. So it's all of that squared. And then, like we've seen before, we subtract off this thing all squared. So b over 2a all squared is b squared over 2 squared, which is 4, a squared, which is a squared, and plus c over a, which of course equals 0. So all I've done here is rewrote this thing highlighted in yellow in the completed square form like this. So what we can do now is rearrange it so we've got this on one side and these terms on the other. So just by rearranging, we're going to have x plus b over 2a all squared is going to be b squared over 4a squared minus c over a. This looks a bit ugly really, so we could actually neaten this up by rewriting this over a common denominator. So I'm just going to move this to the other side now, but think, well, what if I took this c and a and multiplied both numerator and denominator by 4a? If I times both numerator and denominator by 4a, I'd have a common denominator of 4a squared. And so I could rewrite this side all over a common denominator. So then we'd have x plus b over 2a all squared equals b squared. C times 4a becomes 4ac, and the common denominator, as I've said, is 4a squared. So we're getting closer. Next, what we need to do is square root both sides. I know this isn't in the notes as such, but I want to prove it to you sort of organically rather than just having a card sort on its own, so the card sort has a bit more context to it. So square root both sides. So x plus b over 2a all squared becomes just x plus b over 2a. Remember, when we square root something on the other side, we always need to consider the plus or minus. And so we're going to have plus or minus the square root of b squared minus 4ac. So all of this square rooted. Remember, with square rooting fractions, we can square root the numerator, then square root the denominator separately. So if we square root 4a squared, well, the square root of 4 is 2, and the square root of a squared is just a. So it's looking a bit more familiar now, isn't it? But we've still not got x as the subject. And so we can solve for x by making x the subject. Just bear with me as I write very slowly. I apologise if I seem too slow. So just subtract b over 2a from both sides, and as you can see here, conveniently, we already now have a common denominator of 2a. So we can put this minus b when we subtract it all over the 2a. So for the final step, x equals this minus b now, plus or minus the square root of b squared minus 4ac all over 2a. And that is the famous result which we've all seen before. So how does that help us in terms of ordering these cards? Well, like Blue Peter says, here's one I made earlier. Okay, so I've shown you there so you can see all these steps and understand them. What we need to do now is apply this in terms of, here are the steps, what I've shown you. How can we apply this to reorder these cards? Okay, well, if I just go back and forwards, if you bear with me. So we've got these 10 cards to put in order. So what was step 1? Well, I did set out step 1 straight away. I said we've got to set it out like this. So the first step is considering ax squared plus bx plus c is equal to 0. And so the first step is this one. So first step we've got over here. Oops. Done. That's the first step. Second step, we had to get rid of the a, so we divided through by a. And so the next one, step 2, we divide through by a. And so we find this over here. So dividing through by a is this one here. After step 2, we completed the square. So step 3 is this one here. After completing the square, we arrived at this result below. So step 4 is this one in the top left. After step 4, what we did is we rearranged the equation to end up in this form. So step 5 is, step 5 is here. And so on yours, it's that here. After step 5, we put it all over a common denominator. We did this. So that was step 6. Making a pig's ear of this. Unlock that. There we go, step 6. So step 6, put it all under, sorry, all over common denominator. That is this one here, step 6. After step 6, what we did is we square rooted both sides. So step 7 was this. So on our grid here is where it says we can take the square root of both sides. So not many to go next. So after that, we ended up with this result over here, which was step 8. That correlates to step 8 in the bottom left. Then what we did is we rearranged to solve for x. So this step here, I just said we're going to make x a subject, which is a different way of saying we're going to rearrange it. So step 9 is this one here. Oops, no, this one. And then finally, because we end up with this here, step 10 is that we can actually solve this for x. And so finally, step 10 isn't really what we need to put down, but step 10 is just trying to show to you and explain to you clearly that that can be solved. So step 10 is like an extra complementary step, if you like. And so ordering the cards, you should have had them like this. So going down on the left, 4, 3, 9, 10, 8. On the right hand side going down, 2, 6, 1, 5 and 7. Okay, so here's a second activity for you to try next. It's matching parameters. So although the quadratic formula is a useful tool, as it says here, it's essential it's used correctly. So examiners often comment or have commented in the past on students who do not use the correct parameters A, B and C when using the formula. What I'll show you in a moment is how this new Classwiz calculator really makes this incredibly easy. So in about 3 or 4 minutes I'll show you how to do that. But for now, just to understand what the quadratic formula comes from and what constitutes its ingredients, if you like, we're going to just try and match each quadratic equation to the correct set of parameters A, B and C. where a is a coefficient of the x squared term, b is a coefficient of the x term, and c is the constant term when each quadratic is written in the standard form ax squared plus bx plus c equals 0. So try this now. I'll then talk you through how they match up in a moment. So press play when you're ready to see how these match. Okay, well, we're going to match them up now. So this first one here, if we rearrange this, it would have x squared minus 5x plus 2 equals 0. And so a would be 1, b would be minus 5, and c would be 2. And so this one here is going to match to this one at the bottom. This one here is nice and easy. We have 5, 2, and 1. And so we need to find 5, 2, and 1, which is, sorry, minus 1, I can't read, 5, 2, minus 1, which is this one here. Next up, we have minus 1, 5, and 2. So it matches to this one here, which is minus 1, 5, and 2. This one here, we have 5x squared equals 2x plus 1. This needs rearranging. If we rearrange it, we'd have 5x squared minus 2x minus 1 equals 0. So we have 5 minus 2 and minus 1 for A, B, and C, respectively. So this one matches to is this one here. The last one on the left, we have 2, 1, and that becomes 5 when we move this one to the other side. So 2x squared plus x plus 5 equals 0. So after 2, 1, and 5, which you can see as this one here. Now we can move on to the ones on the right hand side. So here, don't get confused and think it's 2, 1, 5. Always start with a coefficient of x squared. So this is 1, 2, and 5. And so we're going to have 1, 2, and 5 over here. So that one matches to this one. Next up we have 1, minus 2, and 5, which is going to match to this one here. Not too many more to go now, as you can see. This one needs rearranging again. So if we add 4x to both sides, we have 2x squared plus 5x, and then subtract this 1 from both sides, gives us 2x squared plus 5x plus 1. So we need 2, 5, and 1, which is this one here. Next up, we need to multiply. This doesn't look like a quadratic right now, but if you multiply through by x, what we'd get is x squared plus 5x minus 2 equals 0. And so we'd have 1, 5, and minus 2 for the coefficients. And so this one matches to this set here. And finally, if we take everything to the right-hand side, actually no, let's subtract 2x squared from both sides. That gives us minus x squared plus x minus 5. So we'd have minus 1, plus 1, and minus 5. So the final one to match goes here. So I hope you got those and managed to get most of those right. If not, hopefully all of them. Moving forward, a few more worked examples now, just using this quadratic formula. And as promised, I'm going to show you how to use the calculator function as well to make these even easier. So, first of all, we've got part A to solve. We have 10 minus 3x minus x squared equals 0. So let's just do it with the quadratic formula first. And so our A, in inverted commas, is going to be minus 1. Our B, in inverted commas, is the coefficient of the x, which is minus 3. And our C is 10. And so now if we plug these parameters into the quadratic equation, x is going to be minus b, so minus 3, plus or minus the square root of b squared. Well, b is minus 3, so minus 3 all squared, minus 4 times a, which is minus 1, times c, which is 10, all over 2 lots of a, so all over 2 multiplied by minus 1. Let's neaten this up now. You could do it on a calculator straight away. I'm going to show you that in a moment. Minus 3, that's 9. Now in this square root, minus 3 all squared is 9. 4 times minus 1 times 10 is positive 40. 9 plus 40 is 49. So that's going to be all over 2 times minus 1, which is minus 2. I've just spotted a random mistake. Ugh, what have I done here? Minus 3 is plus 3. I thought about squaring this 3. I don't know why I do such stupid things. Maybe I'm tired today. I need some excuse for that. Minus 3. Sorry, that's plus 3. Okay, so obviously 49 is a square number, and so if we square root that, we're going to get 7. And so either x is 3 minus 7, which is minus 4. Minus 4 divided by minus 2 is 2. Or it could be that we've got 3 plus 7, which is 10, divided by minus 2, which is minus 5. So those are the two solutions for that. Now, like I say, if you've got one of these, which you should have, what we need to do to solve this using the calculator is to press menu and scroll along until we get to what we can see as equation/func. So press equals when we see this option. It's not a simultaneous equation. A quadratic is a type of polynomial. So press 2. Now it asks for degree, which just is asking for the highest power of x. The highest power in a quadratic is 2. If it was a cubic, it'd be 3. If it were a quartic, that'd be 4. So because we're looking quadratic, we put 2 for squared. We can now type in the parameters manually. So first of all, type in the coefficient of x squared. So here it's minus 1. Press equals. Then type in the coefficient of x. Here we have minus 3, so type in minus 3. Finally, the constant term, which is 10, type in 10, press equals again, and press equals for a second time. It will give you the roots. So the first root, root 1, is 2, press equals again. The second root is minus 5. And more than that, if you press equals again, it will tell you either the maximum or minimum. In this case, the maximum of this quadratic is where x is minus 3 over 2, so minus 1.5. And press equals again, it'll even tell you what the maximum value of y is. So it gives you the turning point of the quadratic as well. So that's just a little aside note to how you can use this Classwiz tool to really help you out with these quadratics and solving them. Makes it so easy. So learn that skill well. Anyway, part B, moving on. We haven't got this in the standard form, so we need to rearrange this to 3x squared minus 7x minus 1 equals 0. Once you've done that, we can see we've got a, which is 3. We've got b, which is minus 7. And we have c. The constant term at the end is minus 1. So now we can just plug this in. So x is minus b, which is minus 7, plus or minus the square root of b squared, which is minus 7 all squared, minus 4 times a, which is 3, times c, which is minus 1, all divided by 2 lots of a, which is 2 times 3. Let's neaten this up. Minus 7 is positive 7, then plus or minus, well, what's in here? Minus 7 squared is 49, so we've got 49, then 4 times 3 times minus 1 is minus 12. 49 minus minus 12 is positive 61. So we have that all over 6. So we're going to have 2 roots, so we can have minus 7 minus 61 over 6. Or the second one, which is minus 7 plus root 61 all over 6. Moving on, we have a couple more things to mention. So the first one is function notation and quadratics in disguise. So a function we can write as f of x. It's just a rule that maps each value of a set of inputs to a single output. So the set of possible inputs for a function is known as the domain. So the domain is just the set of all possible values x is allowed to take. On the other hand, the set of all possible outputs that y can take is called the range. And so the possible values of x is called the domain, possible values of y is called the range. The roots of a function are the values of x for which f of x is equal to 0. And by the way, if the input of the function can be any real number, we can write the domain as x is a member of the real set of numbers. So this is a fancy symbol which just means all real numbers. So let's have a look at a couple of examples on function notation. So we've got two functions here, f and g, defined as f of x is 2 lots of x plus 7, and g of x is x squared plus 8, where x is a member of the set of real numbers. Part A, we need to find the values of f of 5 and g of minus 3. So first of all, for part A, so f of 5 is going to be 2 lots of 5 plus 7, which is 10 plus 7, which is 17. Also g of minus 3. The input here is now minus 3, so we take minus 3 and square it, and add 8. Minus 3 squared is 9, and 9 plus 8 gives us, weirdly, 17. Part B, bit of a trick question you might think, it sort of is. So part B, it says find the values of x for which f of x equals g of x. So we've got that when f is 5, it gives 17, and when g is minus 3, that gives us 17 as well, but that is two different values which just happens to give the same output for both, for one for f and for g, so it's not quite the same thing as what we're asking for here. We're asking for a value which, when you put it into both of these, gives the same output. And so 5 and minus 3 don't necessarily work because we tried f of 5, but we didn't try g of 5, so g of 5 might be different. So what we do for part B, just write it down as f of x equals g of x, and then just remind yourself of what f of x actually is. Well, f of x was 2x plus 7. G of x was defined as x squared plus 8. And so what this is saying is, where f of x is equal to g of x, we want 2x plus 7 to be equal to x squared plus 8, because that's how the functions were initially defined. So all we need to do now is just rearrange this. So if we subtract 2x on both sides, we have x squared minus 2x, then subtract 7 from both sides, we have this standard quadratic. This will now factorise. If you think of two numbers that multiply together to give us 1, but when we add them give minus 2, that's x minus 1 and x minus 1. Minus 1 multiplied by minus 1 is positive 1. Minus 1 added to minus 1 is minus 2. So this becomes a perfect square. So therefore these functions are equal when this bracket is equal to 0, and this bracket is equal to 0 if and only if x is equal to 1. As a double check, try x is 1. 2 times 1 plus 7 is 9. 1 squared plus 8 is 9. So x equals 1 does work. For question 2, these are what's known as hidden quadratics. Okay, and you can spot a hidden quadratic a mile off with practice. A hidden quadratic is one where we have one variable and two different powers of that variable. The main thing we need for it to be a hidden quadratic is where the biggest power is double the other power. 4 is double 2. And so x to the power 4 is x squared squared. Okay? In the same way, the power here is x. If we double x, we get 2x. So this 2 is a hidden quadratic. Okay? So normally quadratics are like this. Plus bx plus c. Whereas here, the power of x on its own is just an invisible 1. 2 is double 1. That's the standard type of quadratic. But it doesn't need to be 2 is double 1. We can have, for example, here 4 is double 2, or 2x is double x. And so these here are actually quadratics, but they're disguised. Hence the term hidden quadratics, or quadratics in disguise. Now, how I would solve them is as follows. I'd make a substitution for the middle term. I'd call whatever the middle term happens to be big X. It then becomes much more familiar looking. So for part A, let's make a substitution. Let's call big X is equal to x squared. Okay, then what we'd have, x to the power 4 is x squared squared. It's just big X squared. Then we have minus 5 lots of big X minus 36 equals 0. This is now a quadratic in big X. So two numbers we need to find which multiply to minus 36 and add up to minus 5. Those two numbers are going to be positive 4 and negative 9. Therefore we can say that big X is equal to minus 4 or big X is equal to positive 9. However, we didn't actually have this quadratic in terms of big X. We need to remember that big X is actually x squared, and so either x squared is minus 4 or x squared is 9. Now, apart from imaginary numbers where we could solve this, if x squared is a negative value, we know in all circumstances this can't happen. This has no real roots, and so we have to reject this one here. And our solutions lie with only this half. So x squared equals 9. What two values give a value of x squared equal to 9? Those two values are obviously either minus 3 or positive 3. So x is either minus 3 or positive 3. That's part A sorted. Part B, again, make a substitution of big X for this middle term. So let big X equal 2 to the power x. Therefore, you have 2 to the power x to the power 2. Power of a power, x multiplied by 2. That gives us 2 to the power 2x, which is what we have here. And so this substitution does work. Okay, so if big X is 2 to the power x, then what we'd have, this thing here is big X squared. So we have big X squared minus 9 lots of big X plus 8 equal to 0. This is now a quadratic in terms of big X, which again factorizes quite nicely. So two numbers that multiply together to give me 8 and add up to minus 9. Those two numbers are minus 8 and minus 1. So therefore we can say that either big X is equal to 8 or big X is equal to 1. Finally though, remember, we didn't have this equation in terms of big X, we had it in terms of little x. So substitute back in 2 to the power x. So 2 to the power x is equal to 8, or we have it 2 to the power little x, sorry, is equal to 1. So therefore, well, 2 times 2 to the power 3 gives us 8, so either x is equal to 3, plus remember, anything to the power 0 gives us 1, and so the second solution is x equals 0. and then we're done. Over to you now. So here's the suggested exercises. Page 21, exercise 2b, just try question 3. Then move on to 26 and 27 pages, question 7 and question 8 on 2e. So try these, check your solutions at the back. If you get stuck, ask me as ever. So work hard on those, good luck, and you'll hear from me again soon. Thanks very much for listening.